Hello, in this video we're going to talk about the ion product constant and how that leads us to pH and our measure of acidity. Alright, so first off, the ion product constant. Now, when we were talking about acids and bases earlier, we were doing these all in water. Generally, water acts as a solvent when you're doing an acid-base reaction, but we also saw that the water would function as an acid or base in the reaction. And in the examples we did before, we had some other component and then water. But what's to say that water can't simultaneously be both its own acid and its base? You take the hydrogen from one water molecule, move it over to the other water molecule, and you get hydronium, H3O+, and hydroxide, OH-. Why not? Turns out the hydrogen atoms in water do hop around and move around like crazy. And they do spend some time as the hydronium and hydroxide ions. So it turns out it does this. This is called the autoionization of water, or the autoprotonation of water, and it leads to small amounts of H3O+ and OH- that we can totally measure. And so the equation's down here on the left. It's an equilibrium equation, just like before. You have two water molecules that are liquid, in equilibrium with hydronium and hydroxide, both aqueous. So when you do the equilibrium constant expression, you just have the products here, the two things that are aqueous, and you don't include the liquid water. So that's pretty straightforward. And so this equilibrium constant is another one of those special ones that gets its own symbol. And so we call this Kw, the ion product constant. You can think of it like K water. And experimentally, the value at 25 Celsius is 1 × 10 to the negative 14th molar squared. But again, I don't so much care about the units. That's a really small number. So that tells you that while this does happen, it's still a very small amount of hydronium and hydroxide for any given sample of water. But this is important because we play with the relative amounts of hydronium and hydroxide when we're going about doing acid-base chemistry. So we have to start here. So here's the critical information again. Now we're going to want to know what the concentration of each of these two reagents are, or I should say each of these two products are. So they're both equal to the same variable, whatever you want to call that. So you just take the square root of the ion product constant, and you find that for just straight up water, you have the hydronium equals the hydroxide equals 1 × 10 to the negative 7th molar. Again, a small quantity, but still one that we can measure. So this is just true, right? Water does this, and it has this slight ionization. It does depend on temperature. So here's a nice temperature dependence of the ion product constant. And later we'll see how you convert this into pH of water. And so the pH of water also changes with temperature. We typically just deal with this at 25 Celsius for a couple reasons. One, the numbers work out pretty, so that's nice. And two, 25 Celsius is a really nice temperature to do chemistry at, because it's a little above room temperature, and it's much easier experimentally to heat something up to keep it at a constant temperature than it is to try to bounce between heating and cooling or cool it or whatever. So 25 Celsius is nice. Alright, then we can use this to define acidic and basic solutions. So a solution that is neither acidic nor basic, we call it neutral, and that would mean that the concentration of H3O+ and OH- are equal. In an acidic solution, you have more H3O+, which, remember, we can also write this as H+, more H+, more acidic. That makes sense. And then a basic solution, there's a greater concentration of hydroxide anion. And so this is our fundamental definition of acidic and basic, and it's a really important thing to know because we use this and then move on with it and assume you know it. So we want to talk about these concentrations. How acidic is it? How much, hydronium ion do you have? And, well, if we do this in molarity, we get these really obnoxious numbers. We're varying between 10 to the negative 15th and 10, and it's so annoying to say, oh yeah, the concentration of H+ is 10 times something to the negative something to the something to the something. What a pain in the bottom. And so we want a more simplified way to talk about this, and so we invented the pH scale. And you've probably heard the phrase pH before. And it's kind of a simplified view of acidity and basicity, but not incorrect in any way. It's just a much more easy way to look at it. And so pH, it's a logarithmic scale. And so what a logarithmic scale does in base 10 is that for every order of magnitude you move, so say you go from 10 to the negative 2 to 10 to the negative 3, that corresponds to a shift in 1 pH unit, a shift of 1 pH unit. So similarly, if you go from 10 to the negative 5 to 10 to the negative 10, that's 5 orders of magnitude, that's 5 pH units. pH, you can think of it as the power of H+, which kind of makes sense because we're talking about the concentration of H+, in a logarithmic sense. So then, 10 to the negative 15th, the exponent there means something. It actually stands for something else, but hey, I'm going to think of this as power of hydrogen because it works. So you calculate pH by taking the negative log. Base 10 here is important. Don't take ln. So you take the negative log of the concentration of H3O+, and that's pH. It's a pretty straightforward thing. Now, this idea extends beyond H, right? So you can have POH, you can have pKa, pKb. So P anything in our chemistry context is the negative log base 10 of anything, whatever that is. I already gave you the suggestions, right? pH, POH, the acid and base equilibrium constants, Ka and Kb, they're again special equilibrium constants that we denote with a different subscript. You can say pKa, pKb, and that's really nice because then you don't have to talk about 1.76 times 10 to the negative 5th. You can just say 4.5 or 4.76 or something, right? It's much easier to talk about. But again, remember, P anything equals the negative log base 10 of anything. You can have P yo mama is the negative log base 10 of yo mama, or for those into rap, you can have P Diddy, which would be the negative log base 10 of Diddy. But it's just Diddy now, because the P was getting in between him and his fans. Then maybe he changed his name again, and who knows. All right, so we're back here. Now we can make a nice little chart of this, right? For all the H3O+ concentrations, calculate the pH. Then pH generally runs on a scale from about 0 to 14. Some people think, that it just stops at 1 or 14, and that's not true, right? You can go below 0, you can go slightly negative, you can go above 14 to maybe 14 and a half, you might be able to push it up to 15, but you're not really going too much farther than that. And then correspondingly, and we'll talk about how to convert between these, between H3O+ and OH- in a slide or two. You can have the OH concentration, what it's equal to, and then again, negative log base 10 of OH gives you POH, and you can write this down. Notice that the pH and POH scales seem to run opposite to each other, as do their concentrations. So if you increase the pH, you decrease the POH, and that makes sense, as we'll see in a few minutes. And again, these numbers are at 25 Celsius. You can tell from this chart that pH plus POH equals 14, and again, that's at 25 C, and we'll talk about why that is in a minute, but that's another important outcome here. Now that we have a way to talk about pH, we can give some examples. Vinegar, orange juice are pretty acidic. So is Coca-Cola, soda, things like that. Pure water is 7. Usually when you get to water, it's a little less than 7, like 6.5, maybe 6, because CO2 dissolves into the water and then converts to carbonic acid, which makes it slightly acidic. But if you didn't have any CO2, you'd be 7 pH. Blood's a little basic, 7.4. And just more natural things tend to be acidic than basic. That's just kind of the way it turned out, I think. And then, again, now with the pH scale, we can use this to define acidic, neutral, and basic. Acidic pHs are less than 7. Neutral, the pH is 7. And pH is greater than 7 or basic. How do we go about measuring this? You can drop some chemicals in there that change color depending on the pH. They're called indicators, and there's a universal indicator, which is a nice mixture of chemicals that covers the whole pH range. That's not very precise, so there are instruments that measure pH. This one is a very much 1980s-esque instrument, but there's nice fancy new ones that do a good job of measuring pH. Now, I already talked about logarithm sig fig rules in a previous video, so I'm not going to go into it again. I'm just going to throw this slide up here. Feel free to pause it and remember how this goes. And if you want, you can look back and find the other video where I discussed this more in depth. And then the same is true for the anti-log sig fig rules, right? This was in a different video. Go take a look. But this is something we need to know because we're dealing with logs and anti-logs when we're working with pH. Okay, so I've been hinting at this for a few slides now, so let's really nail into how do we convert between pH, pOH, etc. So let me make a little grid. pH and H3O concentration, they're related. pOH and hydroxide concentration, they're related. So if you're going to go between pH and concentration of hydronium, well, pH is the negative log of H3O plus concentration, or often we just say H plus, same thing. Now if you want to go the other way, you move the negative sign over to the left, you take 10 to the both sides, and then 10 to the log of H3O plus gives you just H3O plus, and then you have 10 to the negative pH. So that's how you would convert back the other way, just by solving for the other variable. Now the same thing's true with OH, right? pOH is negative log of the concentration of OH, and then you can go back the other way by taking 10 to the negative pOH. Don't forget the negative sign there. It really messes things up if you don't have it. Now, going between the hydronium and hydroxide concentrations, this is from Kw. We talked about this in the beginning, right? That the ion product constant is equal to the product of these two concentrations. And so if you know H3O plus, you know Kw, you can solve for OH minus, whichever way you want to do it. Now, if you take this equation and you take the negative log of both sides, base 10, you'll get something that we call pKw, which pKw equals just 14. So let me erase this because now that's going to confuse everybody. But that's why there's a 14 over there. Then on the right side here, if you take the negative log of this, that's the same thing as saying the negative log of that plus the negative log of this, because that's how logarithm rules go. And then this one becomes pH, and this one becomes pOH. So that's why we can say that pH plus pOH equals 14. And I kind of made a mockery of this on the writing, so just look at the slide, it makes sense. So, a couple examples to finish us off. What's the pH and pOH of 50 millimolar HCl? Well, HCl dissociates completely. Hopefully this is something you learned previously. It'll dissociate into H plus and Cl minus. And now H plus is a bit of a misnomer. What that really means is that the H plus jams itself onto a water molecule and makes H3O plus. Okay, so when we want to find the pH, we take the negative log of the H3O concentration. And well, the concentration of HCl is 1-to-1 stoichiometrically with H3O plus. So we can say we have 0.050 molar H3O plus. Then we take the negative log of that, and we get a pH of 1.3. That's pretty acidic, but definitely something you can make in the lab. All right, then the pOH, the easiest way to do this is just take pOH plus pH equals 14 and rearrange it to say that 14 minus pH equals pOH. I mean, you can do it with the Kw and the product of the two concentrations, and that works just the same. I just find that a little more obnoxious to do, so I like to do this addition-subtraction way. Last example, Coca-Cola has a pretty acidic pH. It's not so great for your teeth, or perhaps the rest of you. But what's the concentration of H3O plus and OH minus in Coke? So here's the pH. Now, simplest to find the pOH from here, so 14 minus pH gives you pOH. Now we can take 10 to the negative pH to find the concentration of H3O plus, and this will come out in molar. And then you can take 10 to the negative pOH to find the concentration of hydroxide. Again, it comes out in molar. I know the units are kind of a mess here and they don't fall easily from the equations, but we kind of define pH to be on a molar basis. So, okay, that makes sense there. Now, if you want, you can double check. You can take the concentrations of the two, multiply them by each other, and you should get Kw. And so we do that here, and it checks out to within experimental precision, and that's all great. So, that's all I have for this video. Thanks for watching.